Hi everybody. So, friction heaters. They represent an ingenious application of the principles of physics and engineering. They're innovative devices that harness the power of friction to generate heat. At its core, friction heating relies on the fundamental concept of converting mechanical energy into thermal energy. When two surfaces rub against each other, the resistance encountered produces heat, and this basic principle is employed in friction heaters, where controlled friction between materials is utilized to generate and distribute heat efficiently. One of the most notable applications of friction heaters is in the field of manufacturing. Friction welding is a solid-state welding methodology very similar to forge welding, and it dates back to the turn of the 20th century, using initially rotary friction welding, which developed as early as 1924 in England and 1929 in the Weimar Republic into something called linear friction welding. It moved into the USA in the 1960s, and in 1962 was used by Caterpillar Inc. It led directly to the process known as friction stir welding and friction surfacing. But perhaps the best known is linear vibration welding, where materials are placed under contact, put under pressure, and an external vibration is then applied to slip the pieces relative to each other, creating a weld. In the automotive world, of course, friction and excess heat are the two major enemies of any car engine, with the brakes being the worst culprit. Efforts are made to reduce the heat in brakes with things like regenerative braking systems, but the excess heat itself was traditionally just lost. However, research at the moment is going into looking at getting the thermal energy back out as electrical energy, because we're talking about 300 to 400 degrees centigrade, depending on the car speed and the applied pressure on the brakes, being the temperature the brakes can actually reach. So attaching a thermoelectric generator to the brakes offers the possibility of scavenging some of this excess heat and turning it back into electrical energy. Friction heaters are finding their way into the realm of consumer electronics, with portable devices such as hair straighteners and curling irons, and even some types of clothing irons employing friction heating technology. These devices utilize the friction generated between rotating and rubbing surfaces to produce the necessary heat for their operation. The benefits of friction heaters extend beyond their practical applications. They offer advantages such as rapid heating, precise temperature control, and energy efficiency. By harnessing friction to generate heat,
and you can have as much stuff, but this is homemade.
These devices minimize energy wastage and contribute to the sustainability efforts. Perhaps the most convincing experiment showing how effective friction was at boiling water comes from John Tyndall in Tyndall's apparatus. Tyndall was an Irish physicist from 1820 to 1893 who poured some water into a copper pipe, rotated it while pressing wood hard against it, and of course it boiled the water and shot a cork from the end of the pipe. Lloyd Tanner was a New Jersey inventor who in 2008 enjoyed a brief spell of fame, notoriety, when he used wooden blocks to boil water into steam that received quite a lot of attention, and we had clips of that device earlier on in this video. But even more famous than Lloyd is Eugene Frenet, who in 1977-78 created what he called a fuelless furnace. This is one from the archive, so please forgive the quality of the video and the sound quality, but I thought it was a simple but effective idea, and of course winter is up and coming, and so are the October fuel rises. They're all imminent. So I thought it was worth reposting, just so that people were aware of it, because it was made such a long time ago, and obviously we have so many videos it can sometimes be a bit difficult to see. So I thought I'd repost it. I hope you enjoy it, and as I say, please forgive the audio quality. The hardest thing about these Frenet heaters is actually fitting the two bodies together, finding them or making them so they have quite a close tolerance. Now, if you happen to be lucky and find two things that have that close tolerance, then it's a piece of cake to make these things. Now you might remember this, it's a food canister, and I made Stirling engines out of them in previous videos, and they're just a stainless steel canister. As it happens, they're just the right size for that. That's a half-litre paint tin, and that half-litre paint tin goes in quite nicely. So if you have two canisters like that, it takes next to no time at all to make these heaters. I made this one, incidentally, in less than an hour. Now all I actually did was mark up the centre of the paint can, and the paint can lid, and drill through a 6mm hole. And what I did in this bottom 6mm hole is put a dome nut, and if you look inside you can see that I just drilled through, put a bit of silicone sealant to stop anything going in there, screwed it down, and that's the bottom made. Now the top, I did exactly the same thing, only used a long 6mm bolt and centred it, drilled through, and screwed that bolt through. Now I've got a lathe, so I turned that down to fit what I'm going to drive it with. If you don't have a lathe, it doesn't really matter, it'll just drive off a drill. You don't really need a lathe to do it. And once you close that up, then that makes a nice sealed container. Now this one has absolutely nothing done to it at all. It's just glued to this bit of board so that I can spin it. And I've attached the thermocouple to it, and you can see the thermocouple reading there on that screen. It's at 14 degrees, and all I actually have to do now is put a little bit of oil in and put the lid on. Now the lid comes like that. It's a bit of acrylic on the steel rim, and what I did with that was center it again, drill a hole through it, and then I put a piece of plastic on there that was at 22mm to take this bearing, and just a bit bigger than 8mm so the bearing came through free. Now all I have to do is slot that on there, and we're ready to go. So if I fill this up with oil and slot that on and attach the Dremel. Okay, the poor little Dremel couldn't cope with it. There was just far too much resistance in the oil. So I was going to use the hand drill, then I thought, hey, why not just move the pillar drill and use that instead? Now this only turns at about 980 RPM, something like that, because it's on the setting for soft metals. So it's going to turn about 980 RPM. I've set it on there, same thing, thermocouples there, drills attached, and I'm going to start the stopwatch. We'll turn it on and watch what happens to the temperature setting. Okay, 5 minutes later it's at 27 degrees. Like I said, this is set really low, so what I'm going to do is change the setting and we'll see if we can get it faster. Okay, so I was wrong. Actually I had it on its lowest setting, which is 580 RPM. So it got up to 27 degrees in 5 minutes at 580 RPM. Now I've got it at its highest setting, it's 2600 RPM, and let's see what it does then. Okay, I'm going to stop it there because it's had 3 minutes, and at 2600 RPM it's gone up to 46 degrees. It's getting a bit too hot to hold. I have to hold it because it'll spin the whole thing unless I hold it as well. But there you go, a really simple Fresnel heater that will run off a drill and get up that temperature actually really quite quickly. And I'm not surprised it's more efficient than the other one I made, because like I just said before, these squat broader shapes are much more efficient than those long thin shapes. Anyway, how to make a Fresnel heater in less than an hour and heat it up to 50 degrees in 3 minutes. I hope you enjoyed watching, and thank you very much. So there you go, that's me 10 years ago. Hopefully the idea was helpful to you, hopefully it was pretty clear. Thank you very much for watching, and please do remember to like and subscribe.